And using Huckel MO, we'll be able to come up with a really, really nice explanation for the existence of this behavior. I probably mentioned it before, but what we'll talk about today is aromaticity. Right. We kind of talked about this a little bit. I think it was a long time ago. We had on a midterm for thermodynamics in the first semester. I had a question about the thermodynamics of aromaticity, where we kind of calculated thermodynamically how much more stable an aromatic molecule is compared to a non-aromatic counterpart. I think I forget what molecule I used in particular. I think butadiene and benzene, and ethylene. So here we're going to approach the topic not from thermodynamics, but rather from first principles, which is the molecular orbitals of the molecules. Right? Thermodynamics is a derived quantity that you get from the quantum mechanical structure of the molecule. Right? So we're going one layer deeper than just measuring changes in enthalpy and stability. Let's actually calculate and look at why aromatic molecules are much more stable than their non-aromatic counterparts. So the motivating example I want to use today is the classic benzene. All right, and we're going to compare the stability of this molecule versus two other kind of base molecules or kind of templates that we can use to compare. One is that we can compare it to three molar equivalents of ethylene. The idea is that benzene is kind of like three ethylenes put together in a ring. Right, so it seems like a reasonable thing. And we'll also look at it versus cutting this in half, or cutting a bond apart. Let's see if I can draw this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Yeah, that's right. Versus the linear version of this molecule, right? Cyclohexatriene, or hexatriene. Right. So again, all of these systems have the same number of pi electrons in them. Right. This one has 6. This one has 3 times 2, and this one has 6 as well. All right. And I want to compare the relative stability of these using molecular orbital theory today. So let's do that. So let's look at ethylene first, because that's the easiest case. We've already looked at it. Again, what we're assuming is that all of these molecules, right, some of the assumptions we're making here. One is that the sp2 framework, the single bonds, are all equivalent. Right, so we're holding everything equal except for the pi system. So the sp2 part, the kind of in a plane, right, the single bonds between all the atoms, so it's all the same, right? Except we have an extra one here that connects these two atoms together. But in general, we can just treat them as the same concept. All right, so that's what we'll do there. Of course, we'll assume all carbon atoms are equivalent. Well, that's not, we can't say that. Well, as we'll see, that's not the case. Let me say that. So we'll construct our MOs from carbon 2pz orbitals, right? The ones that are sitting out of the plane that aren't hybridized, right? And we'll use Huckel theory, right? So we'll just focus on the differences of the pi bonds using Huckel theory. Once we do the math for this, we'll have to set up some matrices and calculate some eigenvalues and eigenvectors like we have in the past. And these are going to be fairly large because there's 6 atoms, so they're going to be 6 by 6. So we'll have a little bit of setup to do, but the analysis will be very straightforward once we get through that math. So let's start with ethylene. That's the easiest one to do. Right, and we've already talked a little bit about how ethylene bonds. That was how we introduced this problem, or Huckel, right, that we have. Again, we're just focusing on the double bond part. Right, and our Huckel Hamiltonian for this There's alpha, beta, beta, alpha. Right? There's only two atoms. Diagonals are this alpha term, and betas are equivalent. They're the nearest neighbor. That's how much they overlap each other. Each atom overlaps each other. How much they talk to each other. And we got that the wave functions for these MOs for the pi system are 1, 1, and minus 1, 1, which is 2pz plus 2pz and 2pz minus 2pz. These are the coefficients on the outside of the atomic orbitals, so I'll rewrite that. So if psi is 1, 1, that means we have a 1 times the wave function for the 2pz orbital for carbon 1 plus 1 times the carbon orbital 2pz and carbon 2. Right? Wherever, it doesn't matter how we label these, 1 or 2. Right? So these are vectors, and these are the coefficients on the outside of the atomic orbitals, and these are our molecular orbitals, right? Plus or minus, if you will. Like that. Those are our two solutions. It doesn't really matter where I put the minus 1, it doesn't matter, there's just flipping the sign. It's completely arbitrary where that minus goes, so I just put it there. Okay, so the molecular orbital diagram of this is really easy. Carbon 2 and carbon 1 on either ends. Our orbitals, our atomic orbitals are at energy alpha, that's by definition. And they split by a value of beta. So we form a bonding MO at alpha plus beta, where we're saying beta is a negative number. Again, that's arbitrary. And there's another one at alpha minus beta, like that. Each of these atomic orbitals provide one electron. They're half-filled orbitals, p orbitals. So the total combination has both of the electrons in the bonding orbital. Okay, so that's ethylene. Right, we've already seen this. Now we can derive a quantity. Right, we're talking about stability here. Right? Aromaticity is about the fact that benzene somehow is more stable than either of these molecules, either equivalent in terms of when you remove their pi bonds. The double bonds are stronger in benzene than they are in these cases. That's the hypothesis. That's what aromaticity is. So the question is how much energy is contained in those pi bonds? How much energy when you put into the system to break them? Right? And that's not a hard calculation to do here. So the energy of the pi system, the total pi system, is going to be the sum over all the electrons, right? All the electrons of their individual energies. Okay? And their pi bonds, right? So each of these electrons, so we'll call this 1 and 2 or something like that. E1 is just the energy of that orbital times 1, right? There's one electron at energy alpha plus beta. And of course, there's another one at alpha plus beta. Well, I'll just write it like this. E1 and E2, these are our two electron energies. Right, so those are our two electrons, and so the total pi energy is E1 plus E2, which is 2 alpha plus 2 beta. Okay? So that's kind of again, these numbers don't mean anything to us because they're qualitative. But you can kind of think of this as the potential energy stored in those electrons when they're in this molecular orbital. That in order to remove them completely from the atom, to break the bonds completely, you need to pump in 2 alpha plus 2 beta energy in order to remove them. Okay. So let me write that down, because we'll come back to that number again. So the energy of ethylene is 2 alpha plus 2 beta, right? And there's 3 of them. Right, the equivalent, we're going to compare benzene to 3 of them, right? So we'll have to multiply that by 3 at some point to compare it to benzene. The idea is that benzene is 3 ethylenes put together. So let's just hold on to that fact for a second. This is 2 alpha plus 2 beta. Okay, so that's kind of we're going to kind of use that as our energy basis, right? That an ethylene gives us that much energy. It's the electronic energy of the pi system, and now we're going to compare what the energy of this system is and this one as well. And what we'll see is that they're not all equivalent, as they shouldn't be. Okay. So let's go ahead and set up the next problem. Let's look at hexatriene, 135 hexatriene. So let me see if I can draw this kind of nicely. Something like that. And I'll label the atoms just to keep things consistent so we know what to write. When we construct our MO and when we interpret its results, we know which atom is which. So we'll count left to right. 1, 2, 3, 4, 5, and 6. Okay. And now we just have to construct a matrix for this, a Hamiltonian matrix, Huckel and Mo of alphas and betas. And let's remember the rules again. Hij, which is the ith row in the jth column of the matrix, is alpha if I is equal to j. Right? So along the diagonal is alpha. Beta if I equals, so j equals I plus or minus 1. That's the neighborhood, that's the neighboring. Sorry, j equals, I plus or minus 1. Beta, that's if they're neighboring atoms, they talk to each other, and then 0 otherwise. Right, that's our nearest neighbor approximation, that only the atoms close within one bond apart are the only ones that overlap each other. Okay, so we have alphas along the columns. So let me go ahead and mark the rows here just to keep things nice and organized. We have 6 alphas here. 6. Okay. And now we need to put the betas in somewhere, right? So, for instance, 1 only talks to 2. Right? So there's no other connections to 1 besides 2, so there's a beta here, like that. And likewise, there's going to be 1 for 2 and 1, like that. And the rest are zeros for row 1, 2, 3, 4, right? Because 1 only talks to 2. I'll write the rows, the columns here just to keep things clear. All right, so then we got to finish the rest of the matrix. Of course, now 2, when we talk about row 2, the columns again are the atoms nearby it. So 2 talks to 1, that puts a beta here. But 2 also talks to 3, so there's a beta here, and the rest are zeros. And you can see that this pattern continues, right? If we go to 3, it talks to 2 and 4. If we go to 4, it talks to 3 and 5. And so all of the alphas are kind of escorted along a row by the betas, and everything else are zeros. Missed the beta here, sorry. This is for, hold on, 1, 2, 3, 4, 5, 6. So there's a beta here, 0, 0, 0, 0. There's a beta here, and then 3 zeros. Okay, well, I haven't really arranged my matrix particularly organized, but that should give me all the numbers I have. I have six elements in each row, 6 columns, and there's betas that are flanking each side of the diagonal. Right? And of course, on 6, there's only 1 beta, just like there is in carbon 1. There's only 1 beta because 6 isn't connected to 1. Right? So there's no beta here on this at this corner because 1 and 6 don't talk to each other. Okay. So again, we can just pump this right into Wolfram alpha and calculate the eigenvalue, all the wave functions, and so on and so forth. But I will give you the answers here once I find them. I'm going to go ahead and erase this over here. So again, now we have 6 p orbitals that we're adding together in a linear chain. Well, let's go ahead and calculate it with Wolfram alpha. Why don't we just do that? Maybe it's more instructive that we do it manually and then write down the results. So I'm going to go ahead, we have 6 atomic orbitals we're combining, so we should expect 6 wave functions of molecular orbitals back. So I'll go ahead and write them here. Let me do it like this instead. Sorry, let me move them over a bit so everyone can see. I'll bring the screen up in a second. All right, so these are our 6 molecular orbitals that we need to calculate. Ignore this. This is me just testing it. Now let's go ahead and put in that matrix. So again, remember all you have to do is type in eigenvalues and eigenvectors, and then put the matrix in with squiggly brackets. So we have A, B, and then 4 zeros for our first row. The next row is going to be B, A, B, and 3 zeros. Oops. Our next row is going to be 0, B, A, B, 0, 0. Our next row is going to be 0, 0, B, A, B, 0. Is that right? Yep, that's right. Our next one is going to be 0, 0, 0, B, A, B. That's our 5th row. And then our final row is 0, 0, 0, 0, B, A. Okay, so let's make sure we got that right. We have A and B and a bunch of zeros, BAB, 3 zeros, 0 BAB, 0, 0, 0, 0 BAB, 0, 0, 0, 0 BAB, 0, 0, 0, 0 BA. All right, cool, we're good. Okay, so let's look at the results of this. That gives me a bunch of crap. Did I get this wrong? Hold on a second. I shouldn't get imaginary answers. Hold on a second. Why is it giving me imaginary answers for? That looks right to me. Looks okay to you?
Yeah, it's just the benzene one, but missing B's. Because the molecule is 1 and 6 aren't connected.
Right, 1 and 6 aren't connected, so it should be good. Why is it giving me imaginary results? This should give me real results because it's symmetric. Oh, why is it not
We put in that matrix so many times for benzene.
Yeah.
It's basically the same thing.
Well, in benzene you're going to have
Yeah,
B's in the
B's
corners,
are-
right?
it's
That's the
same
only
thing.
difference.
That's the only difference. That should be working. I don't know why it's not.
Let me try something different. See if it does this diagonalized. Okay, it doesn't like me. Let's try real eigenvalues and eigenvectors. See if it'll work. It should give me a real result because it's symmetric and positive. So, okay, it just looks at my real and thinks it wants me to talk about that. All right. Well, anyway, I have the answers here. I'll have to figure out why it's not doing that. Weird. Very strange. It should give me maybe 0, 0, 0, 0, maybe. All right, I'll have to go back and double check why it's not doing it. So let me show you what the actual results are. I have them written down. I'll have to figure out why it's not doing that. I made a typo. I don't see. Okay, so yeah, so the results of these are like this. So I'll write these in matrix form. 0.23, 0.42, 0.52, 0.52, 0.42, 0.23. So that's the symmetric combination of all of them. That should be the lowest energy orbital. The energy for this one is alpha plus 1.8 beta, approximately. I'm going to round that a little bit, but the next one, and we'll draw these in just a second, is 0.23, 0.42, sorry, I screwed that up. I apologize. All right, this is 0.42. All right, I missed the order. I apologize. This is 0.52, and then 0.23 minus 0.23 minus 0.52 and minus 0.42. Okay, I apologize for that misordering. Okay, you might notice interestingly that there's a plane of symmetry in these, and we're going to see these kinds of planes show up in these numbers. You kind of see if you reflect this across this axis, the numbers are symmetric. Here they're positive, and here you have an anti-symmetric combination like that. So this molecule is the same on one side and opposite on the other one in this case. The sign changes here, so this is a node. There's a nodal plate between those two atoms, which means that they don't overlap in this orbital, right? That they cancel each other out in the middle of the molecule, if you will. All right, we're going to see more of those as we go up, of course. The next one, the energy of this, is alpha plus 1.24 beta. All right, you can see that your beta is a negative number, so this is a smaller negative number than this one, so we're starting to go up in energy. The next one's going to be 0.52, 0.23, negative 0.42, negative 0.42, positive 0.23, positive 0.52. And again, you can see again that there's a symmetry there in the middle of the atom molecule. This side is the same as this side. But there's two sign changes. There's one here and there's one here between carbons 2 and 3 and carbons 4 and 5. There's a sign change. Also, there's two nodes here. All right, we'll draw these out in just a second as well once I finish writing them down. And then psi 4, 0.52 minus 0.23. This is minus 0.42, and then 0.42, 0.23, and minus 0.52. And again, you can see there's a symmetry here, but now it's anti-symmetric. This is the same as this, flip mirrored, but with the flip signs. We've gone from the symmetric, this is even, odd, in terms of function. We'll see that once we draw them out. They have this nice symmetry to them, as they should. The next one is 0.42, minus 0.52, plus 0.23, plus 0.23, and then it's going to be minus 0.52 and 0.42. All right, again, this is a symmetric combination. We mirror it between the halfway through the molecule. You have the same on the opposite side, right? So this is interesting. The even number ones are odd functions, and the odd number ones are even functions, and that's just enforced by the fact that we have 6. We have a matrix, a 6 by 6 matrix that's symmetric. So you're going to get these planes of symmetry. These are super important once you do the analysis a little more carefully. And then we're left with our last one, where the sign changes every time we go across every time we change an atom, the signs cross. 2, 3. All right, now forgot to write the energies down, so let me write those down real quick just to have them. This one, E3, is alpha plus 0.47. Write that again. 47 beta. And this one is, I'll write it above it, E4. It's actually this one, but the sign's changed. It's minus 0.47 beta. All right, so now it's higher in energy, right? Beta's negative, so that means it's higher than where we started. And the rest of them, you can imagine, this one, if these flip here, then this one, number 5, is the energy of 2, but with a negative sign. And then 6 is this one with a negative sign. Okay, this is 6. All right, so there's a lot of numbers. But we can interpret this immediately and draw molecular orbital diagrams of each of these. So let's do that. Again, a lot of numbers, but we can interpret it very, very, very easily. All right, these numbers, again, are the coefficients of that atomic orbital's contribution to the molecule. Right, so what this means is that every molecular orbital has a contribution from each of the atoms. There's no zeros here. Right? So every vector is a combination of each of the 6 pi orbitals, p orbitals on each of the atoms. And you can see there's some symmetries involved with all of this because, again, this is a symmetric matrix. You would expect symmetric eigenvectors as well. Right? Everything's kind of kosher. Everything's kind of the same. So we have 6, so we start with 6 2p orbitals on carbons. Right? Each one has 1 electron in them. Right? And we form 6 new molecular orbitals. And notice for each bonding orbital, we have an anti-bonding orbital corresponding at the opposite energy, or the opposite distance from alpha, right? We have this one and this one. These are the bonding, anti-bonding combination. 4 and 3 are the bonding, anti-bonding combination of each other, and so on and so forth. So for every line I draw down, I'm going to draw an equal and opposite line in the opposite direction. So we have one here. This is psi 6, psi 1, psi 2, psi 3, and then we have the same thing, psi 4 and psi 5. Like that. Okay, so there's our 4 molecular orbitals. We know what their energies are. This is alpha plus 1.8 beta. This one is alpha plus 1.24 beta. This is alpha plus 0.47 beta. And then the rest of them are negative. Minus 0.47 beta. Alpha minus 1.24 beta. And alpha minus 1.8 beta. Okay, so those are our 6 molecular orbitals, and we can draw them very quickly, very easily. Right, what I'm going to do is I'm going to draw a straight line with 6 different points. 2, 3. Maybe it's better if I draw the structure instead. Right, I'm going to draw like that, and we can draw the molecular orbitals, what they look like by taking these coefficients and then just drawing the coefficient, and the size of it tells you the size of the contribution of the orbitals. So the smaller this number, the less it contributes. And the sign tells you which way it's pointing. Let me draw this a little bigger. Okay, so here's our first orbital right here, psi 1. You can see that the ones on the exterior, 1 and 6, are the smallest. Right? So that means that they contribute the least. So there are small little, maybe it's easier if I just draw it in a straight line now I think about it. But you can do it however you please. It's probably easier to draw it like that. So we'll call this our little, we'll say positive is in this way, that the shaded lobe is pointing up. And it has the smallest number, 0.23. Okay? And then the next atom is 0.42. That means its orbital contribution is about 2 times the size in the same plane, or in the same phase. So it's got a little bit bigger of a contribution. There's 2. And then the third one, if you see, 0.5 is 0.52, it contributes the largest contribution to the wave function. So its lobe is the largest, like that. And then you can see it's symmetric across the middle of the molecule, right? Because the next 3 are exactly the same but mirrored. We can immediately write it like this. We know that the next one is going to be 0.52. It's going to be big. The next one's going to be a little smaller. And the final one is going to be a little tiny boy, like that. All right, so there's our first molecular orbital. Right? I've drawn them kind of roughly to scale their contributions. And they're all the same sign, right? So this is a really nice bonding orbital, right? They're all overlapping. They're all sharing electrons. Right? This is a classic pi orbital. There's no nodes, right? Any electron is shared. The electrons in this orbital are shared amongst all the atoms, but in general, most of them, they exist more near the center. Right? The atomic orbitals that contribute the most are the ones in the middle. And so if you think about what's the probability of finding one of these electrons in this atom, or in this molecule, well, they're most likely going to be in the middle. Right? So this is kind of the bonding orbital that really defines the middle part of the molecule. Right? That's where most of the contribution is. Biggest contribution. So we can put 2 electrons in there, as we do. So let's go to the next one. Again, it shouldn't be too hard. Let me write down 6 circles. 1, 2, 3, 4, 5, and 6. And now we can write the coefficients on this one. Now they go from medium, large, small, and then they change signs in the middle. Okay, so I'll draw my medium ones on the edge. Like that. And notice that on the edges 1 and 6, they're flipped. So this one is positive, and this one is negative. And then we can draw a bigger one at the second entrance, the second atom, and the 5th atom. This. And then we have the ones in the interior. They're the smallest contributions, and they have their signs flipped, like that. Okay. So again, what's happening now is that now there's a node or plane at the middle of the atom where the electrons don't share each other, right? So if an electron's in here on this side, it's never going to be on this side. Right? There's no connection between the 3rd and the 4th atom here because there's a node between them. So the electrons in this orbital, psi 2, tend to sit on the exteriors and don't exchange across each other like this. So typically that electron again is going to be localized near the edges because that's where most of the lobes are, right? The largest contributions are on the ends here. So the electrons in this orbital are going to sit near the ends and not in the middle. You can imagine that if you're doing some sort of chemical process on this molecule and you want to attack it in the middle, like you want to add something to the middle of this molecule, you want to attack that pi bond, well that's going to be really hard to do because the electrons that define that pi bond in the middle of the molecule are really deep in energy. They're not really all that accessible. And what we'll see is when we start to get to the middle of the middle energies of the molecular orbitals, the ones where the HOMO and the LUMO are, they tend to exist on the edges. Right? You can see that here. In psi 3, the next one we're going to draw the largest contributors of the exterior atoms. So let's go ahead and draw number 3. 1, 2, 3, 4, 5, and 6. In psi 3, again, as I said, the largest contributors are the ones on the exterior. They have the same sign. I'm going to go work inwards. The next ones are phase matched with each other, positive, positive, and it's a small one. A little small one here that's positive, and another small one here that's positive. Like that. And then we're left with 2 medium-sized ones that are of an opposite sign. So here's our little medium ones, and they're an opposite sign, this. Right, so how many nodes do we have in this molecule now? Where how many times the sign change? Well, the sign changes here, and it changes here. Right, so just as a notice, we have 0 nodes in the most lowest energy. We have 1 here, and we have 2 here. Right, this is really telling. Right, the more nodes, the more places the sign changes, the more places where the electrons can't be shared across all the bonds. Right, where you have these probability cutoffs where the probability is 0 in the middle. That's what that means. Nodes being probability 0 at that point. The more nodes you have, generally the higher energy your orbital is. That's because it's less bonding. Right? Here you can share these electrons with all the atoms constructively. That's very stabilizing. But as we start to go up, we get more nodes. The electrons in these orbitals are more localized. Right? They can either be here, here, or here. They can't cross. And so that leads those orbitals to be higher in energy. Right? And you might expect as we keep going, this is going to have 3 nodes, 4 nodes, and 5 nodes. And we're going to keep seeing that. But as we go up higher in energy, we get more nodes. All right, so let's go to the next one. And again, we have 6 electrons. So we've completely filled up, right? So our system started with 6 electrons. We filled them all up. Right? So we're already done with all the bonding, all the MOs that have filled electrons in them. So this one is the HOMO, H3. Right? And these are going to be the LUMO. All right, so let's look at the LUMO real quick. Side 4. 1, 2, 3, 4, 5, 6. The edges are the largest again. Again, it looks very similar to side 3, but the signs have changed. But the edges are the largest, but they're opposite sign now. All right, and then we're left with the next ones are the smallest, and they're sign flipped. So this one, let me make a really small one here. This, and the sign is flipped. The next one is the medium one. Let me just do it for this other one. This. Again, that one's positive. Right? Positive 2, 3 for 5. And then our middle ones are minus point. The medium ones flipped in sign as well. But they're matched with the ones on 2 and 5. So that's going to be a medium one. Just like this. Like that. Okay, how many nodes do we have? Well, we have one here. We have one here. And one here. Right, there are 3 nodes, just like we expected. Notice that the HOMO and the LUMO, their largest atomic contributors are the ones on the exterior. These 2. Right? The HOMO and the LUMO are on the exterior. Right? These are the electrons that are most accessible to any external molecule. Right? These are the ones that require the least amount of energy to move, if you will. Right? Either to remove them completely or to excite them. Right? These are the ones that are chemically accessible, if you will. And the chemically accessible electrons in hexatriene are the ones on the edges. Right? So typically what you would expect, and this is what organic chemistry bears out, reactivity, that when you react hexatriene with something, the pi system, say you're going to do an elimination or some sort of substitution or addition to that double bond, that tends to happen on the edges. The most reactive atoms are the ones on the edges of the molecule and not the interior ones, because the electrons that sit in the interior are low in energy. They're hard to get to. Right? You need a lot of energy to pull these electrons out. So the middle bond is quite inert in hexatriene, and it's actually the ends that tend to be the most reactive because they're the ones that are most have the most contribution in the HOMO and the LUMO. All right, when we come to next class, we'll look at these interactions, HOMO and the LUMO interactions for reactions between different types of double bonded systems, and that will be borne out very clearly. Right? These end atoms really play a big role in the reactivity of these molecules. All right, so let me just finish up the drawings. 1, 2, 3, 4, 5, and 6. So side 5, we have medium, large, small, with alternating signs. So I'll go ahead and just draw them and then we'll color them in. that. Side 5, we have positives on the ends. And then the next ones in the interiors, flip the sign. And then the next set, the internal set, are both positive. All right, so where do we have nodes? Well, we have one here, we have one here, and one here. 4 nodes. Right, so the majority of the kind of where the electrons sit in this, if you had electrons in this atom, in this molecule, in this molecular orbital, excuse me, if you had electrons in here, well, they would almost act like lone pairs. Because if you put an electron in here, it would basically sit at most likely in the region where you have the highest atomic contribution, which is right here on these at carbon 2 and carbon 4. Right, they're the largest contributors, and they don't really talk to the other atoms, right, because they have nodes between them. Right, so if you put an electron in this, they would be largely localized on carbon 2 and carbon 5. Right, so that actually tells you something about the reactivity of this molecule. If you could get these electrons excited, the system's going to effectively, if you excite one electron, say to here, and if I take this electron and put it here, well, then this electron is either going to be here or here. It could be either place or equivalent. Right? And so this molecule kind of looks like, let's see if I can draw it, kind of like, that's on 2, sorry. It's on 2, and then you have something like that, right? So if you were to excite that electron, you would have a resonance structure. Of course, it would be equivalent on the other side, like this. And if I were to have a system where one of those electrons from the HOMO is excited up to this orbital, right, it would look like it would react like a radical, just like this on number 2. Right? I don't need to know anything about the molecule. I don't need anything quantitative. All I have to do is look at these orbitals and say, well, these atoms have the largest contribution, and they're kind of by themselves. Right? They don't share electrons with anything else. So the characteristic structure for a molecule with one electron in this orbital will look a lot like this radical, right, at the 2 or the 5 position. Right? And that automatically tells me that if something comes in like OH, like an OH radical, right, it's gonna react at that 2 or 5 position, right, if the system's in that state. Right? So I can already predict some sort of reactivity for this system just by looking at these orbitals. All right, and then I have the last one. The last one, the sign changes on every single one. Small, medium, large. So that's really easy to draw. I'll draw it over here to the left. 1, 2, 3, 4, 5. Small on the edges, medium in the middle. Did I miss some? Sorry, I missed one. 2, 3, 1, 2, 3, 4, 5. Yeah, there we go. And then 2 big ones in the middle. Yeah. And then the sign changes between all of them. And there's nodes between every single atom, so there's 5. Right, that's obviously going to be the highest energy one. There's no bonding interactions at all there. They all cancel each other out, right? There's no this orbital, basically, if you put an electron in it, it's going to stick to one atom and one atom only. It's not shared amongst all the other carbons, 2p orbitals. So this is the true antibonding orbital, if you will. Right? This is very antibonding, right? It's by definition the opposite of a bond. Not only do you not have any constructive overlap, all of the overlaps are destructive. Right? So it's by definition the most antibonding orbital. Okay. That was a lot of qualitative work, but we're done. Right, we now understand, we have a good picture of what the orbitals of the pi system for this molecule looks like, and now we can calculate the electronic energy of it. Right, what's the total energy of this pi system, the potential energy? Right, so we have 2 electrons in each of these first 3 orbitals, so the total energy of the pi system is going to be 2 times the energy of these electrons, alpha plus 1.8 beta. And then 2 times the energy of the next one, 1.24 beta, plus 2 times alpha plus 0.47 beta. Right, we're just summing up the individual energies of each of the electrons. So that's 6 alpha plus some beta. I think I have the number here somewhere. Yeah, I do. 6.988 beta. Okay, so we've done a lot of work just to get to this number, but here's something that's very interesting. Right? We can already make an interesting claim. The energy of this system is 6 alpha, let's just say roughly 7 beta. Okay? It's not exactly 7, but it's close enough. And then the energy of 3 ethylenes is 6 alpha plus 6 beta. Now notice what has happened when I've gone from 3 separate double bonds to a set of triply conjugated bonds. Right? All I've done is connected 3 ethylenes in a linear chain. And now my pi energy is lower by 1 beta. One value of beta compared to ethylene. Right? This is our kind of generic case. 6 alpha plus 6 beta for that energy. Right? And then when we connect all of them together so that they can share their pi electrons, we get an additional stabilization of 1 beta. Right? This is conjugation. Right? This is the definition of conjugation. Right? The idea that allowing double bonds to share their electrons with each other is an inevitably stabilizing effect. Right? That this implies that just by connecting the 3 together, you get an additional beta of stabilization, which is really cool because the only thing that's different between these 2 molecules is that you've substituted these hydrogens for carbons. Right? So you have these carbon bonds instead. Right? So you're only changing the sp2 framework of the molecule. Like going from here to here is changing just the sp2 framework. Right? You're just tacking 3 single bonds between 3 double bonds, 3 double bonded systems. Maybe I should write it in the middle here. So they're only connected by single bonds, but we've put them all in the plane so that they can share their pi orbitals. Right, all the pi orbitals are planar or parallel to each other on each of the atoms. Right, and that somehow has actually brought us an extra beta of stabilization. All right, so you can imagine that if I continue this, if I go from 3 to 4 to 6, I keep adding more and more chains to this. This beta, the total beta is going to get equivalently more and more stable relative to the equivalent number of ethylenes. Right? This is the idea of conjugation. The fact that we're able to, by connecting groups of pairs of pi orbitals together, we can infer an extra bit of stabilization out of it. Right? So this molecule, by definition, is 1 beta more stable than 3 ethylenes. Right? Any questions about that so far? Okay. All right, so we're about halfway there. So now we just have to do benzene. Right, now the question is, now all we have to do is now we have one more single bond we're connecting, right? We're connecting these 2 atoms together, effectively. Of course, we have to change the geometry a little bit to get a hexagon, but all we're doing is just adding a single bond here between the 2. So how does that provide addition? Will that provide additional stabilization with respect to hexatriene? Okay. I'm going to go ahead and erase all of this. We have to do it again for benzene. Benzene's numbers actually, because of its hexagonal shape, actually the numbers are much simpler. We don't have as many fractions. Actually, all these kind of numbers are actually square roots. Right? Turns out they're square roots of 6, square roots of 5. square roots of 6, excuse me. So those are kind of ugly. But when we make it, interestingly, when we enforce the 6-fold structure of benzene, these numbers and the orbitals, the numbers simplify dramatically. It's actually kind of cool. Let me pull up my benzene. And if I'm lucky, it will actually work on Wolfram alpha as well. Okay. All right, so let's do benzene. So let's go ahead and label our atoms. Start from there. Again, it doesn't really matter where we start because it's a ring. It's completely arbitrary. All right, so what is our matrix for this? Well, again, it's a 6 by 6. 1, 2, 3, 4, 5, 6. Again, it makes my life easier if I just label the rows and the columns, just so I don't get rows and columns mixed up. Again, we have alphas in the middle, on the diagonal. That. And the only difference between hexatriene and benzene is now the atom is connected on both sides, right? This molecule is a chain or a loop, so it just keeps going. So again, 1, let's look at the row 1 for atom 1. This atom, it's connected to 2 and 6, so we'll put a beta there and then a beta at 6. And the rest of these are zeros. We can keep doing that. 2 is connected to 1 and 3. 0, 0. 3 is connected to 2 and 4. So we have a 0 at 1, a beta at 2, a beta at 4, and zeros. 4 is connected to 3 and 5. So a beta there, and zeros everywhere else. 5 is connected to 4 and 6. We have a beta here, and 3 zeros. And then we're at 6. 6 is connected to 1, so there's a beta here. 6 is connected to 5, so there's a beta here, and then there's 3 zeros. 3, like that. The only difference between this and the interesting thing is the only difference between this and hexatriene, this is the exact same matrix, except these values are 0 in the linear case. You can look at that. The only difference between these two molecules in terms of its matrix is just those corners, because 1 and 6 are connected. That dramatically changes the structure of the molecular orbitals. Just one little term. And what we're left with, so our wave functions now, let's draw them over here. I'll write them over here. Let me just write this, save this for later. Psi 1 is really easy. It's 1, 1, 1, 1, 1, 1, 6 ones. Just a second. Yeah, it's okay, sorry. Psi 2 is 1, 2, 1, minus 1, minus 2, 1. Like that. Psi 3, interestingly, has a different structure. It's minus 1, 0, 1, 1, 0, minus 1. Put some zeros in there. Psi 4 is 1, 2, 1, minus 1, minus 2, minus 1. And again, you can see that symmetry across the middle of the vector. Psi 5 is an interesting one. it has, it's effectively 1, 0, minus 1, or sorry, let me read this off one more time. Sorry, yeah, 1, no, we're sorry, let me change the signs here. Sorry, minus 1, 0, 1, minus 1, 0, 1. And size 6 is just ones, but they change sign every one. So it's 1, minus 1, 1, minus 1, 1, minus 1. Okay. The energies of these are surprisingly very simple. This one's alpha plus 2 beta. These two are degenerate. These are alpha plus beta. These two are alpha minus beta. And this one's alpha minus 2 beta. All right, so instead of having these square roots and these fractions that we have, these irrational numbers that we have here, or rationals, we have nice integer numbers of everything here. So that really simplifies our math quite a bit. So our structure now, again, we have 6 p orbitals that we've constructed these from. They all have 1 electron in them, 6 2p carbon orbitals. And we form a bonding combination at alpha plus 2 beta. And then we have 2 orbitals that are at alpha plus beta. They're degenerate. Right? And then we have the opposite combinations, right? With the negatives instead. Alpha minus beta and alpha minus 2 beta. Like that. Right? That's busy. So now we fill it up. We have 6 electrons. 1, 2, 3, 4, 5, 6. This is our HOMO. And this is our LUMO. Okay, so let's draw them. Let's go ahead and let's do a quick drawing of all of these. So psi 1 is 1, 1, 1, 1, 1, 1. So those are really easy to draw. I'm going to, instead of drawing p orbitals, I'm just going to draw little spheres. You can imagine they're p orbitals. And I'm just looking at it from a bird's eye view, so it looks like that. Edge on. Of course, the orbitals are pointing out of the board, so there's a negative component pointing into the board, but I'm just looking at it from bird's eye view. And then psi 2 and psi 3, they're degenerate, but they have quite a bit different structures. This one has contributions on all the atoms, and this one only has it on some. So there are specific nodes in this system. So let's look at psi 2 first, the first one. Oops, sorry, let me draw that. Okay. Remember, we count from 1 and clockwise, from the top left and go clockwise. Psi 2 is 1 here. And then notice the carbon 2, which is at the tippy top, is twice as large. So we have a big contribution here, and then a smaller contribution here. And then if we look at the other atoms, they're, did I miss a term here? Hold on a second, psi 2. Sorry, this should be minus 1 as well. I apologize. Minus 1. And so the other side of the atom, 4, 5, and 6, they're all negative, so they're the opposite sign, but the same magnitudes. Right, so this one has 1 node through it right there. Where the electrons that are destructively, the orbitals are destructively overlapped across these 2 bonds right here. And psi 3, did I count that right? So let me see. We should also do 3, 6. Yeah, that's close enough. All right, and then the other one, psi 3, there's minus 1, 1, and a 0 in between them. So there's a negative there. There's nothing here in the top, and then there's a positive lobe here. And then psi 3 has a connecting lobe that's the same, a dot, and then a connecting lobe like that that's the same. So minus 1 on 6. Okay, so these overlap across these bonds, these overlap across these bonds, but you have 2 nodes. Effectively, you have 1 here. You have 1 there. Sorry, just 1 there. 1 plane there. So each of these have one plane of nodes, if you will, one line that you can draw between the 2 contributing parts of the molecular orbital. This one has 0. This has 1. So let's go to the next set, side 4 and side 5. And you can probably guess what these look like just by inspection. There's a negative here, a big lobe here and here, and little ones on the other side. Lobes here are positive on the edges and negative on the other side. So there are 2 nodes in here. There's one that goes like this, and one that goes like this. Right? So there's 2 nodal planes in this orbital. And then the other one, the other orbital that is degenerate, psi 5, has zeros on this atom and this atom. The 2 edges in this case, and the sign between the other lobes is equal and opposite, like this. Okay, so there's the other one of that set, and again, there's 2 nodes. There's one here, and there's one here. Right, 2 nodes. All right, and we're left with the last one, psi 6. That one's pretty easy to draw. They're all flipped. None of them overlap with each other as they shouldn't. This is the most anti-bonding combination. They all have components. The electrons are shared amongst all of them, but they're not shared between them. Like that. Right, and how many nodes do we have here? We have 1, 2, 3 nodes, 3 nodal planes. Right, so again, we see the same kind of structure that we saw with the other molecules. The most bonding orbitals have no nodes. There's a set that has 1 node, 2 nodes, and then 3 nodes. And again, the energies aren't as destabilized relative to beta as hexatriene, because instead of having 0, 1, 2, 3, and 4 nodes, we have 0, 1, 2, and 3 nodes. Right, so these antibonding orbitals aren't quite as antibonding as these, because this has 4 nodes and this only has 3. Right? So by connecting the atoms together, we've somehow, just by definition, stabilized the molecule overall, because now even our antibonding orbital isn't quite as antibonding and repulsive as this one is. Okay, so again, here's our HOMO and our LUMO. And so let's go ahead and calculate the energy of this. Right, we're already done for benzene. The energy of the pi system is going to be 2 times alpha plus 2 beta, plus 4 times, there's 4 electrons, alpha plus beta. Right, so that's 6 alpha plus 4 plus 4, 8 beta. So benzene, the energy of its pi system is 6 alpha plus 8 beta. Right, now look what's happened. 3 ethylenes by themselves, total energy of all their pi electrons is effectively 6 beta. Hexatriene, we've conjugated those three pi systems, the 3 double bonds together into a linear chain. We've stabilized it by an extra beta. And then we connect the system so that you now have a ring, and you stabilize it by an additional beta. Right? This is aromaticity. That's all it is. That there's that by completing the circuit, if you will, right? By providing a linear a loop for the electrons to be shared around, right? So instead of for hexatriene, you can imagine the electrons are on a highway, if you will. It's not a really great interpretation of quantum mechanics, but bear with me. Hexatriene, imagine your electron here. You're going to be transported across this to the other side. Now, how do you get back to the original point? Well, you've got to go backwards again, right? So the total action, or the amount of distance an electron has to move in a bonding system in hexatriene is large, because it has to go from here to here and then back again to complete the circuit. Right? But in benzene, if you start here, you can go around the loop and come back to the beginning. Right? So if I travel from here to here, from atom 1 to atom 6, I don't have to go backwards like I do in the linear chain. I can just go right here. Right, so now I've completed a concentric loop for our electrons to transport around on. And this provides an additional stabilizing force. Right? So let's look, for instance, just kind of quickly, just at our structure. Right? By adding that additional bond between atom 1 and atom 6 and completing the loop, if you will, my number one bonding orbital, the most bonding orbital, is now stabilized by 2 beta, which compared to hexatriene is 0.2 beta more. Right? So that loop, if you will, that extra orbital interaction between atom 1 and atom 6 adds an additional 0.2 beta to my bonding interaction. Now, but if you notice though, it's a little harder to interpret because now the second bonding orbital in hexatriene is 1.24 beta, but here it's beta, right? So these are actually higher in energy on the same scale as that does. But contrary as well, your electrons, but the advantage is that even though you have 2 electrons at 1.24 beta here, you also have 2 at 0.47. Right? So, but here they're all at beta, so this ends up winning out. Right? So you have an additional advantage of 4 beta here versus, what is this? Is about 1, a little less than 1, and this is 1.5. So this is about 3.5 beta or so right here. Right? So there's an additional half a beta of stabilization or so in these orbitals. It's actually a beta, I think, because you get, yeah, something like a half a beta. Half a beta. So the effects, the stabilizing effects for benzene just kind of add up slowly, but it leads formally to a stabilization of about 8 beta. All right, and so actually this is a really useful calculation to do, because what I can go do is go do this reaction, right? This is what we did on that midterm so long ago, is we added 3 equivalents of hydrogen and created this and asked the question, what's the enthalpy of reaction for this, right? To hydrogenate all the bonds. And then we compared it to 3 ethylenes plus 3H2 to give us 3 equivalents of ethane. Right? And there's going to be a difference between these two, and that difference is 2 beta. So the difference between these is about 2 beta, right? Because it takes 6 beta to remove all the pi electrons effectively from this system, or to take them to their atoms, or just to the single bonds. And here it takes 8 beta for benzene for the equivalent process. So the difference in the enthalpies of the reaction is about 2 beta. And so you can actually go and measure beta really easily this way. If you know the enthalpies of reactions for these two, you can calculate beta. And beta tends to be somewhere on the order of about minus 0.7 eV. And alpha, again, is around the orbital energy of the 2pz orbital for carbon. And this tends to be around minus 12 eV. Okay, so beta is kind of small. Right, but what this says is that you get that this reaction is more exothermic. 3 ethylenes to 3 ethanes is more exothermic by about 1.4 eV, right, 2 beta. Right, and that should make sense, right? If it takes more energy to remove the double bonds, then your enthalpy of reaction should be less exothermic. This should be more positive, because it takes more energy to break those bonds than it does for ethylene. Right? So this ends up being a stabilizing effect, and it leads to a nice measurement of these numbers. And in general, carbon 2pz interactions are all kind of around this number. This is a pretty good number, typical for carbon-carbon. Right, and we can get that that's really nice to get that number. You can get that number very easily by just measuring the difference of these enthalpies. There are many other ways to do it. For instance, I can take one of these electrons and excite it. Let's do that really quick. We'll shine a light at benzene to excite one of its electrons. Like that. And how much have I changed that by? right? It's about an energy of 2 beta, right? Because you're taking an electron in alpha plus beta and moving to alpha minus beta. So the energy difference is 2 beta. And this turns out for benzene is the wavelength of this is about 280 nanometers. It's in the UV. It's about 300 maybe, give or take. And this is equivalent to an energy difference of about 0.7 eV, as we expected. Okay, so there's lots of ways to measure beta quantitatively, right? To make this a quantitative model, we can measure absorption spectra, right? We can measure where the first excitation of the electron happens, the home of the LUMO transition. Benzene has a very bright one around 280. And you can get a nice number for that, right? Or you can do it from thermodynamics. Right? And this is all enthalpy. This is all what aromaticity is. There's nothing more special about it, other than that when you complete a circle, or you complete the loop, if you will, you get an extra little bit of stabilization because now you've included. Right. So here, in the bonding orbital of hexatriene, you have 2 orbitals that have the same sign, but they can't communicate to each other because they're 5 atoms apart. But in benzene, you get an extra overlap across the 1 and 6, right? This is carbon 1 and carbon 6. You get an extra one that you don't get in hexatriene, right? And that just gives you an extra beta, right? Comparatively, right? And that's aromaticity. It's as simple as that, right? It just arises from the fact that when you put the system into a loop, especially a symmetric planar loop, a cycle, if you will, that's a really, really advantageous arrangement for a molecule because you get this additional stabilization in these orbitals. Right? So, in fact, this concept of orbital stabilization came way after aromaticity. Aromaticity was first noticed in the 1800s because people noticed this, that hydrogenating benzene released less energy than 3 equivalents of ethylene. Right? They knew this was C6H6. That's basically all they knew at that point. Right? This is C2H4. Right? And they could say, okay, well, I could do these reactions. These should be roughly equivalent. But now I'm off by some amount, and they're like, okay, that must mean benzene is more stable by some amount because this is less exothermic. And they said that must be aromaticity, right? That there's something to do with this ring system or this combination of ethylenes together that thermodynamically stabilizes the system. And it wasn't until the 30s or the 40s when molecular orbital theory became kind of mainstream by people like Linus Pauling. It's actually a big American invention. Gilbert Lewis and Linus Pauling, Robert Mulliken, these are American quantum mechanics, American chemists that really came up with molecular orbital theory. And they basically show this very simple approximation, right? That the reason why benzene is so stable compared to its analogs is nothing more than the fact that the symmetry, the 6-fold symmetry of the ring, provides an additional set of overlaps between the atoms, and that provides just enough stabilization that causes it to be more stable than its linear counterpart. How much time do I have left? Okay, so this doesn't apply for everything. So in fact, this was on our midterm. If you compare cyclobutadiene versus butadiene, the same argument, but for 4, you'll find that this is higher. This is unstable, right? We've already showed that it's unstable for very obvious reasons, and this is much more stable. So it's opposite, and we call these anti-aromatic. Right? So it's the opposite of aromatic. Again, you can do the same analysis we did for hexatriene and benzene, and you would show that butadiene is actually more stable by about a beta or 2 beta than butadiene is. So it's the opposite effect. And of course, what that leads to is Huckel's rule, which maybe you learned in Orgo 1 or Orgo 2. Right? That Huckel's rule. Rings, conjugated rings with 4n plus 2, which is either so that's either 6, so that's or 10, 14 pi electrons, and our planar are more stable than their linear counterparts. Right? We call these aromatic species. And those with 4n electrons, so that's 4, 8, 12, and etc., the other even numbers, are anti-aromatic, which means that they're less stable than their linear counterparts. These rules will come into play next class. Right? We can actually take this one deeper. All right? And then what we're going to start thinking about is how do we take these systems and how do they interact with other pi systems? What if we bring two pi systems together? How can we predict how? We know what their orbitals look like, so we should be able to predict their reactivity. All right? So we're going to use Huckel theory on Thursday to finish up by taking two pi systems together and look at their reactivity. Can we combine them together? How do they combine? Do they have certain types of geometry or expectations that we have? Are we even able to? And these rules about 4n electrons and 4n plus 2 will come into big use for us in predicting those things. All right, so we'll look at that on Thursday, and that'll close us up, I think, for the semester. If we run over, I feel like we need to talk a little more. Maybe we'll meet on Monday for a little bit, just to clean things up. But otherwise, we have one lecture left. Thank you all.